Having examined using a heap to implement a priority queue, we will discuss one application of a priority queue, which is to implement a sorting algorithm. We will conclude with a discussion of Java's implementation of the priority queue. Any implementation of a priority queue can be used to implement a sorting algorithm. Let's explore why that is true. The elements of a priority queue must be an ordered type, one which implements the comparable interface, which means that any sort implemented with a priority queue is a comparison sort. Because a priority queue is a partially sorted structure, it is a natural sorting mechanism regardless of how it's implemented. The sort involves a succession of n queues followed by d queues, which will produce a list sorted in descending order. The priority is the sort key. There are several ways to implement a priority queue. The choice of implementation influences the efficiency of the sort. The one portion of the code in our heap queue sort example that warrants examination is the algorithm that uses the queue to perform the sort. This code is a private method in the heap queue GUI class. The sort method accepts an array list of integers and returns a sorted list. The priority queue implementation that is used is the one implemented with a heap. When we examine the UML diagram, you will see that either of the other implementations could be substituted for it without changing the behavior. That should also be apparent from the fact that the reference type is the interface type priority queue interface. So this declaration is another example of programming to an interface. The local variable output is the array list that will be returned. The core of the algorithm is in a try block, which handles the exceptions that the queue can throw. As previously mentioned, it involves two loops. In the first loop, the numbers in the array list input are successively enqueued onto the priority queue. The second loop dequeues the numbers and adds them to the array output, and the array list is returned. The remaining code handles either exception that is thrown. Before we run this program, let's examine the component classes and interfaces. The heap queue class is the one that implements the priority queue that we are testing. Although these two classes are not in the program that we will run, either of these two classes could be substituted for the heap queue class without affecting its behavior. The reason is that all three classes implement the priority queue interface. The methods defined in the interface can throw both exceptions. Finally, as has been true with most of our examples, the interface to this program is defined by a GUI that this class implements. Let's run this program and input a sequence of numbers just to confirm that indeed it does sort correctly. So it doesn't matter whether I put in the same number twice, doesn't matter anything about the order. And once I enter these numbers and I click the button, I should see them output in descending order, which is exactly what I see. Next, we compared the three implementations of the priority queue and how they correspond to actual sorting algorithms. We begin with the correspondence. Had we substituted the unsorted array queue for the heap queue, the sort that would be performed is very similar to a selection sort. In a selection sort, the smallest element is repeatedly selected and swapped with the next element of the list. Using the sorted array queue would produce a sort very similar to an insertion sort. With an insertion sort, each element is repeatedly inserted into its proper position. Finally, and not surprisingly, using the heap queue produces a sort similar to the heap sort. Next, we compared the three approaches by examining the efficiency of the two operations. When implementing a priority queue with an unsorted array, the enqueue operation is the simpler one, because the new element can be added at the end of the array, which can be done in constant time. The dequeue operation requires more work. The entire array must be searched to find the element with the highest priority, and then the last element can be swapped with it, so there are no unused positions. To find the smallest element requires examining them all, which is why this operation is linear. Assuming that we are doing a combination of both operations, the average is still linear. Using a sorted array shifts the work to the enqueue operation. Inserting an element in its proper position involves examining at most all the elements, so it is linear. The trade-off is that the dequeue is simpler, provided we keep the highest priority element in the last position. In that case, the last element is just removed and returned. The average is as before. Recall that a heap is a partially sorted structure, which puts it somewhere between unsorted and sorted. So it should not be too surprising that the work is evenly split between the two operations. Both are log n, because as we have seen, both operations only examine one branch of the tree, whose length is log n. The advantage is that the average now is better than both other approaches, which is why this implementation is the best choice in most cases, and the only one most programming language frameworks provide. Let's watch an animation of the heap sort to help us better understand the connection to the heap priority queue. So when I run the sort, what you'll notice is as the nodes turn red, elements are being enqueued. Once all the nodes have turned red, what it means is that this tree has been turned into a heap. Once it's been turned into a heap, the highest value is always in the root. So the succession of dequeues is swapping the value in the root at each point with the next red node at the bottom of the tree. So the nodes are turning blue from bottom to top. And as they turn blue, what you'll notice is that at this point, these values are all in sorted order. And once it completes, the entire tree is sorted. We conclude our discussion of the priority queue with a discussion of what is provided in the Java collection framework. Recall that the linked list class implements the queue interface because it is intended to be used as a first-in, first-out queue. The Java priority queue class implements the same interface. As we've already seen with the first-in, first-out queue, there are two methods for each operation. The methods for enqueue are offer and add, and for dequeue, poll and remove. Java provides only one implementation. That implementation uses a heap. The reason is that, as we've already noted, it is best on average. There are other possibilities. If we knew in advance that we would use mostly enqueue or mostly dequeue operations, one of the other possibilities could be more efficient. We have already considered using an array, but an array list or a linked list are also possibilities. And as with an array, they could be either unsorted or sorted.